Good morning, this is Dr. Jingbo Liu. Today we are going to finish your chapter 4, the major classes of chemical reactions. What we are going to focus on today will be the acid-base reactions. And we are going to learn what's the definition of acid and base and how the reaction is going to happen. You are going to learn 3 different types of the balanced reactions, such as molecular equation, total ionic equation, and net ionic equation. And then we are going to learn the oxidation reduction reactions. It's also called redox reaction. In this part of chemical reaction, we are going to focus on the oxidation number assignment and how do you determine and calculate the oxidation number for the element in your compounds or in your ions. And then we are going to learn about balancing chemical reactions based on half reaction. If time permits, I'm going to be briefly reviewing the redox reaction sequences. Which element is more active, which one is not. Actually, we already know in your periodic table, your group 1 elements, they are more active. Your lithium is also very active. It's the most reactive metal. And then we are going to touch base on the reversibility and the equilibrium states. Again, today's focus will be mainly on acid-base reaction and oxidation reduction reaction. In order to understand the acid-base reaction, we need to know what is the acid and what is the base. In terms of the acid and the base, you have 2 types of acid. One is called weak acid, another one called strong acid. In terms of the base, also you have weak base and strong base. For an acid, the definition is the acid is a substance that produces proton ions. When this substance is dissolved particularly in water, the reaction can be written down as the HX reacted with water produce protons, or sometimes we also write it down as hydronium, H3O+, like what we showed you in this chart. And then you produce this proton, which is in aqueous, and also an X negative. This X negative is called the conjugate base of your acid. For the strong acid, this reaction is going to be completely completed. The substance is going to subject to the complete dissociation, produce proton and its conjugate base. Weak acid, this chemical reaction is going to be partially completed towards the forward direction, meaning this reaction is going to be dissociated in a certain degree. So this weak acid is also known as a weak electrolyte. Similarly, for your base, in terms of the strong base is a substance which produces hydroxide ions when it dissolves in a solvent, particularly in water. The reaction can be written down, generic reaction can be written down, MOH dissolved in water produce M+ in aqueous and hydroxide. If it's a strong base, this reaction will be completely completed. This solution will be a strong electrolyte. On the other hand, if you have a weak base, the reaction will be partially completed towards the forward reaction, meaning the reverse reaction is also going to occur. So this weak base is also a weak electrolyte. I want to indicate or point it out the hydrogen plus the proton ion usually existed as associated hydronium ions. We mentioned as H3O plus because the hydrogen plus the cation ion interacts very strongly with the water molecule. Your water molecule oxygen end is partially negatively charged. Partially negatively charged the oxygen end is going to be attracted by the proton called ion dipole intermolecular forces. Therefore, in the aqueous solution, you barely really see a proton, but an hydronium. In terms of the acid base, I put the strong acid, strong base in this table 4. There are several commonly used strong acid and strong base. Strong acid included hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid, and so on. Strong base, sodium hydroxide, lithium hydroxide, potassium hydroxide, calcium, strontium, barium hydroxides. The commonly used weak acid, such as hydrofluoric acid, phosphoric acid, sulfurous acid. So H2SO3 is a weak acid. Be careful. H2SO4 is a strong acid. H2SO3 is a weak acid. And your acetic acid is the commonly used household vinegar aqueous solution. So acetic acid CH3COOH. A very commonly used base is called ammonia. This ammonia is commonly used weak base, partially dissociated. As we mentioned in the previous class, we mentioned the electrolyte. Your electrolyte can have strong electrolyte and also can have weak electrolyte, can have something we call the non-electrolyte. In terms of the strong electrolyte, meaning this solution or this electrolyte can conduct electricity very well. And this strong electrolyte is going to subject to the complete dissociation of your strong acid and strong base. Usually strong acid, strong base are strong electrolyte. They are going to be dissociated completely in an aqueous solution particularly. The weak acid and weak base, they partially dissociated in a very little, small portion into the cation ions and its conjugate base or conjugate acid in the aqueous solution. The weak electrolyte also conduct electricity poorly. So that's the difference between strong and weak electrolyte. In terms of the acid and base, we need to know something called neutralization reaction. Acid and base, they can react with each other. They neutralize each other. So how do you write down the acid-base reactions? For example, if you have hydrochloric acid reacted with potassium hydroxide, what is your plan to complete the molecular equation, total ionic equation, and net ionic equation? So here is our plan. Usually, you are going to determine the reactants, a strong or weak acid or base. Are they strong or are they weak? That's number one. You can use the table 2 as your guideline. And then you have the product in both of the acid-base reactions, in A, B, and possibly C. They are going to produce water and associated ionic compounds. You can call it ionic salts. First of all, you write down the molecular formula accurately for your acid and the base from your reactants, and then you are going to recombine cation ion and anion to form new combinations. You are going to determine whether this new combined product is soluble or not. That's your plan. Our second question, question B, strontium hydroxide reacted with perchloric acid. You also have barium hydroxide reacted with sulfuric acid. The last one, C, you will take it home. So let's see, what's our solution? In terms of the hydrochloric acid reacted with potassium hydroxide. So here is your solution. First of all, write it down, the molecular equation. So you have your HCl aqueous reacted with KOH, potassium hydroxide, strong acid, strong base. In this case, they're both in aqueous. If you have weak acid, weak base, you write it down as themselves. They are not going to be dissociated. They react, they exist as if they were intact. They were undissociated. And then your chlorine, chloride, and your potassium, they are going to recombine, form potassium chloride. And your OH, hydroxide, and proton, hydrogen plus, and your OH will recombine to form your water molecule. Be cautious, your water molecule always existing as a liquid. Make sure water always as a liquid. Total ionic equation can be written down by dissociated acid base into the associated ions. HCl break it down to hydrogen plus, chlorine becomes chloride, both in aqueous. Potassium hydroxide becomes potassium K plus aqueous, and hydroxide OH negative. Make sure you have a negative sign, negatively charged. And then your hydrogen plus and the OH recombine to form a water molecule. Similarly, your potassium and your chloride, they are going to produce potassium chloride. Potassium chloride is an aqueous solution, is a soluble compound. Therefore, you break it down to potassium and chloride. From this reaction, you find two, spectator ions. Which two are the spectator ions? Your potassium in reactant, potassium in product. Therefore, you eliminate your potassium. Similarly, your chloride in product, your chloride in reactants, you eliminate the second ion, chloride. So you produce your night ionic equation. Hydrogen plus proton in aqueous plus hydroxide in aqueous produce H2O in liquid. So again, here I want to emphasize this H2O must be written down as a liquid, not aqueous, not solid, unless it's the ice, unless it's steam. So you have gas, which is steam, you have ice, solid. So otherwise, if it's not specified, your water will be liquid. The second question, strontium hydroxide is written down as a SrOH. The reason is strontium is from your group 2, therefore your Sr will be 2 plus. Your hydroxide is 1 plus. Your hydroxide is 1 minus, so this is 2 plus. Your strontium 2 plus. Your hydroxide usually is a negative 1 in charge, is an anion. Therefore, your formula will be SrOH2. This higher atomic, the strontium has a higher atomic number when it's bonded with hydroxide. This hydroxide tends to be soluble, yes. And you reacted with 2 moles of perchloric acid, which is also is very strong acid, also very strong oxidizing agent. You are going to recombine hydrogen plus and hydroxide to produce 2 moles of water, because you have 2 of this hydroxide from your strontium hydroxide, 2 moles. And the proton, you also have 2 moles. You produce 2 moles of water. Your strontium perchlorate will be also formed. And then you are going to break down all the aqueous solutions. Any substances you labeled as AQ, you break down them to the associated ions, cations and anions. what's going to happen? Your hydroxide and your OH, they are going to react to form H2O. 2 moles form 2 moles of water liquid. Strontium and your perchlorate, they are the spectators. So you can eliminate your 2 spectators, strontium 2 plus and perchlorate. You are going to receive your night ionic equation. So you found you have 2 moles, 2 moles, 2 moles. Therefore, this number 2 can be removed. You can simply divide it by 2 for all the coefficients. So you have proton plus hydroxide, both in aqueous, produce 1 mole of water, which is a liquid. This is how you write down the acid-base reaction. How about the second chemical reaction, which is called oxidation-reduction reaction? It's also going to be simplified as a redox reaction. It's a redox reaction. In this redox reaction, you have 3 key points. These 3 key points always occur together. Number 1, oxidation is the loss of electron. Loss of electron, people also call it LEO. Oxidation reaction involved in the electron loss. Your reducing agent normally loses electron or electrons. This reducing agent is going to be oxidized. Your LEO is the nickname of your reducing agent. So again, our reducing agent has a name of LEO, meaning that half reaction is going to be called oxidation reaction, involved in the electron loss. Second key point, your reduction reaction. Reduction reaction is the gain of electron. Somebody also call it GER, G-E-R. For me, I really just suggesting everybody focusing on this LEO. Instead of focusing on 2 directions, focusing on 1 half reaction. The second one you think oppositely. If you have the chemical is going to gain electrons, this chemical you call it oxidizing agent. Your oxidizing agent gains electron or electrons and is going to be reduced. In terms of electron loss and electron gain, you need to know the total number of electrons. Your redox reaction involves in the electron transfer, loss, and gain, meaning oxidation and reduction reaction occurs simultaneously. If one substance gains electron, another one must lose electron. For example, if you have magnesium, metal, and oxygen, your magnesium tends to give away 2 electrons, and your oxygen tends to gain the electrons. Therefore, magnesium loses 2 electrons, becomes magnesium 2 plus cation. Oxygen gains electron, becomes oxide. So positively charged ion, negatively charged ions, they are going to form an ionic compound, magnesium oxide. This is the lattice structure for your magnesium oxide. So this chemical reaction involved in the electron transfer. Totally 2 electrons has been transferred. Electron has been lost by magnesium. Electron has been gained by your oxygen. Therefore, your magnesium is called what's the agent? Reducing or oxidizing? Thank you. Magnesium is called a reducing agent. Oxygen is an oxidizing agent. Total number of electron transferred, 2. For both reaction, half reaction reduction and oxidation reaction, total number of electron transferred must be balanced. So that's essentially about the ionic compounds. In the future, you are going to learn about covalent compound. The covalent compound, let me briefly mention, you don't really have electron transfer, you have electron sharing by 2 different elements. Later on, we are going to study it. And then in order to understand the number of electrons lost or gained, we need to know the rules for assigning an oxidation numbers. First rule, called the general rule. Second rule is more specific. Rules for the specific atoms or periodical table groups. First part, general rules. Point 1. For any atom in its elemental form, any element by itself in the elemental form, the oxidation number is 0, no charge. For any monoatomic ions, the oxidation number is the same as the charge. For example, if I have my sodium Na+, this is a monoatomic ion, so the oxidation number for the sodium is the same as its charge. It's called positive 1. For your oxide, O2 negative monoatomic ions, this monoatomic ions has an oxidation number -2. That's how you determine the oxidation number for the monoatomic ions. If you have polyatomic ions or polyatomic compounds, what you are going to do? You are going to do this. The sum of the oxidation number for the atoms in your compound equals to 0. If you have a compound, the charge is 0. The sum of oxidation numbers equals to 0. If you have a polyatomic ions, the sum of oxidation number of your atoms in that atomic ion equals to the ion charge. We are going to show you an example a little bit later. The specific rules. First one, for group 1A. Lithium, sodium, potassium, cesium, including hydrogen, they usually, in most of the compounds, they are +1 in charge, such as sodium, +1. Group 2, beryllium, magnesium, calcium, strontium, etc., they have the oxidation number +2 in all compounds. For your hydrogen, if you combine with a non-metal such as HCl, such as H2O, the hydrogen has an oxidation number +1. If oxygen combined with metal hydride can be -1. Sometimes it can be non-stoichiometry. There is one element that fluorine in what you studied, all the compounds will be -1 in charge. Oxidation number is -1. Oxidation for fluoride is -1. One is bonded with metal or non-metals. For your oxygen, you have two cases. If you have an oxide, if you have the oxide and the other compounds, normally the oxygen has -2. If in your peroxide, H2O2, hydrogen peroxide, the oxygen has an oxidation number -1. If oxygen combined with fluorine, oxygen has a positive charge. So that is very rare, so we are not going to discuss it. For your group 17 or 7A, your highlights: fluoride, chloride, bromide, iodide, fluoride, chloride, bromide, iodide. All of these iodides, when they combined with metals, they normally -1. Unless they combined with oxygens, such as your hypochlorite, hypochlorite, chlorite, perchlorate, such as this Cl, O negative, ClO2 negative, ClO3 negative, ClO4 negative, all of them, your oxidation number for this chlorine or any other halides, you need to calculate it. Use the sum of your oxidation number equals to the charge. Whatever the charge is. For the compound, the charge will be 0. For the -1 will be -1, -2 will be -2, etc., etc. In terms of the terminology of your redox reaction, I want to show you in this summary, the summary of the terminology for the redox reaction. Point 1. If your X is going to lose electron, something else, Y, must gain electron. This electron considered the transfer electron if you have metal, non-metal. Otherwise, two nonmetals involved in the shift of electron or sharing the electron. X loses electron. X has been oxidized. This X is the reducing agent. X oxidation number has been increased. On the other hand, your Y gains electrons. Y has been reduced. This Y is called oxidizing agent. Oxidation number for this Y has been decreased. That's about some key terminologies in your redox reaction. So followed by let's practice on the oxidation number determination, either in the compound or in the oxides or some other acids. For example, I have 3 examples for all. Zinc chloride, sulfur trioxide, nitric acid. What's your plan? In order to determine the oxidation number for each element in the compounds or in the acid, how do you determine it? What's the plan? Plan 1. The oxidation number for the ions in the polyatomic ions must be added up to the charge of the ions. Such as your zinc chloride. Zinc has 2+. Zinc has 2+. Chloride, -1 charge. So the oxidation number, +2, -1, must be neutralized, added up to 0 because zinc chloride is neutral and a neutral compound. Here is our plan. Our solution based on the plan. For your zinc chloride, most of the chloride halides, when they combined with metal, normally is -1 in oxidation number. So zinc, if you go to the periodic table, zinc is in 2B or 12. That zinc can lose 2 electrons. Therefore, zinc +2. Sulfur trioxide. If we didn't specify the oxides, you consider it as oxide. Sulfur trioxide is already telling you the oxygen is oxide. If the oxygen is oxide, the oxygen has an oxidation number -2. Yes, in this case, oxidation number is -2. And then you are going to use the sum of oxidation number. Just assume X is the oxidation number for sulfur plus -2. Totally, how many oxygens you have? Yes, you have 3 multiplied by 3 equals 0. And then you solve for X. X represents the oxidation number for your sulfur. So this oxidation number for your sulfur, my calculation is +6. Usually, oxygen in most of the compound has oxidation number -2. The third one, your nitric acid. Nitric acid, your hydrogen, most of cases, oxidation number +1. Your oxygen, if we didn't specify it, consider it -2. Hydrogen, +1, oxygen, -2. And then this nitrogen, you assume the oxidation number is X. Therefore, +1 plus your X and plus your oxygen, oxidation number -2, totally you have 3 oxygens. So multiply by 3, the oxidation number, adding them together, the charge is 0. You solve for X. My solution, X is +5. That's how you determine the oxidation numbers. If you already know the oxidation numbers, assignment, how do you balance the chemical reaction? In other words, how do you know the oxidation-reduction reaction occurs or not? If there's some reactions, is this reaction an oxidizing reduction reaction? In other words, is this reaction a redox or not? How do you determine it? Your plan is you need to assign the oxidation number for each element. And then if you are going to see the oxidation number change, meaning you are going to have the electron transfer, that reaction will be your redox reaction. Otherwise, if the reaction occurs, but there has no oxidation number change, your oxidation number O dot N dot, oxidation number has no change, stays the same. The reaction is not oxidation reaction. Some other reaction, such as this reaction, the number C, could be we call the double replacement reaction. Reaction A is a combination reaction. How do I know? Let's see. Oxidation number for your oxygen, -2. For your calcium from group 2, +2. Oxygen for your carbon dioxide. For carbon in carbon dioxide, oxidation number for oxygen -2. Oxidation number for carbon, I found this +4. Sorry for that. Carbon has +4. Based on this oxidation number determination, what you see, there is no oxidation number changes for any of the substances. Therefore, the reaction A is not a redox reaction. Reaction A is a combination reaction. Reaction B, let's see. In your potassium nitrate, oxygen -2, potassium +1, nitrogen, you can solve it +5. And you produce potassium oxide, potassium still +1, oxide -2. You produce a nitrogen. Nitrogen is a gas, is an element by itself. Any element by itself has oxidation number 0. Oxygen by itself, oxidation number 0. Therefore, oxygen and nitrogen both subject to the oxidation number change. Nitrogen changed from +5 to 0. You consider this potassium nitrate is reduced. Oxygen increased from -2 to 0. This potassium nitrate is also oxidized. This one is called a self-oxidizing reducing reaction. The number C, sodium +1, potassium, hydrogen +1, your sulfur +6, oxygen -2. Similarly, sodium still +1, oxygen -2, hydrogen +1. So everything when you calculate it, all the oxidation numbers has no change. Therefore, this reaction C is not a redox reaction. Reaction C is also just simply called a double replacement reaction. How do you balance your reaction? Your reaction can be balanced just based on the number of electron transferred. You need to assign the oxidation number for all atoms. And then you are going to identify the reactants which are oxidized, the reactants which may be reduced. And then you are going to compute the total number of electron transferred. So you can do this way. You can draw the tie line. The tie line in the future, you draw something like this, lose 2 electrons, and some other substances gains, for example, gains 3 electrons. And then you need to balance this 2 and 3 by make it to 6. So you are going to compute the number of electrons transferred. So you can draw the tie line from reactant atom to your product atom to show the change. And then what you are going to do, you are going to multiply the number of electrons by an integer to neutralize this electron gain and loss. The total number of electrons gained or lost must be the same. And then you are going to use the related factor. What this factor is, you related this factor to balance your coefficients. And then you are going to double check whether your atoms are balanced or not. And then whether the charge are balanced or not. And then you make sure you are going to specify the states of the reactants and the product. Let's see, for example, I have a copper solid reacted with nitric acid, aqueous, produce copper nitrate and nitrogen dioxide and H2O water liquid. This reaction is not balanced. I want everybody use the oxidation number method to balance the reaction. So here is my solution. First of all, you are going to assign the oxidation numbers for the different element. Copper by itself, 0. HNO3, hydrogen positive 1, nitrogen positive 5, oxygen negative 2. And then you produce copper nitrate. Nitrate, again, this NO3 negative 1, therefore meaning your copper is positive 2. Nitrogen positive 5, oxygen still negative 2. In your nitrogen dioxide, nitrogen has positive 4, oxygen negative 2. In your water, hydrogen is positive 1, oxygen negative 2. Meaning your hydrogen and oxygen, they did not subject to the oxidation number change. Which one involved in the oxidation number change? Your copper from 0 becomes to 2+, meaning you lose 2 electrons. And your nitrogen from positive 5 to positive 4, so meaning you gain 1 electron. Totally, how many numbers of electron has been transferred? Totally have 1 electron transferred. However, in this nitrate, you have something which is not involved in the oxidation number change. So therefore, this second part, this part, you need to multiply. The one gains electron called the reduction reaction. You multiply by 2. You multiply by 2, and you figure out there's 2 nitrogen has no change in terms of oxidation numbers. 2 plus 2, therefore, this nitric acid you need to multiply by a factor of 4. And then your water, you have totally 4 hydrogens. This one you need to multiply by 2. And then you are going to double check whether your molecule is balanced or not in your total reaction. The answer is possibly but no. This nitrogen you also need to balance it into 2. This is a 2 nitrogen, there's 2 more nitrogen, totally 4. Let's double check whether the reaction is balanced or not. Here is what we are going to do. Number 1, you use these tie lines to represent the oxidation number change for copper. From 0 to positive 2, you lose 2 electrons. You can simply do this, 2 minus 2 electrons. This copper has been oxidized. Copper by itself is a reducing agent. And then this nitric acid from nitrogen to nitrogen dioxide. Nitrogen, this is positive 5 to positive 4. You gain 1 electron, meaning this nitric acid, this whole reactant has been reduced. And then what you are going to do, you need to make your electron loss, electron gain to be the same. meaning the second part you need to multiply by 2. When you multiply by 2, so nitrogen dioxide multiplied by 2, but be careful, there are 2 more nitrogens which are not changed. You are going to inspect how many total nitrogens you have. So I have 2 in my reactant, I have 4 in product. Therefore, this number 2 need to multiply by 2. And then you are going to double check on your copper. Copper is 1, your copper is balanced. Nitrogen 4 balanced, oxygen. So you can do this. You can double check. So 2 times 3, that's 6 oxygens, right? And then you have, sorry for that, 4 times 3. 4 times 3 meaning you have 12 oxygens. Totally 12 oxygens. So you have 6 here. You have 2 times 2, 6 plus 4. Somewhere you must have 2 more, right? Therefore, your water need to multiply by 2. And simultaneously double check your hydrogen. So you have 4 times 1 hydrogen, they have 2 times 2, 4 hydrogens. Therefore, your balanced reaction has been completed. Again, in this reaction, make sure the total number of electron loss must be the same as total number of electron gain. And then you make sure your items must be balanced. Also, the phases of your substances must be identified particularly. So that's about the balancing chemical reactions. I do have a couple more of balancing reactions such as lead sulfide going to be oxidized to produce lead oxide and sulfur dioxide. You need to learn how to use these oxidation number methods to balance the reaction. I will leave this chemical reaction to everybody else. Also, later on, we are going to learn lots of chemical reactions. In the chemical reactions, particularly you dissolve your compounds into water. For example, if I'm going to dissolve my sodium chloride into water, what's going to happen? Sodium becomes to positively charged ions, Na+, and your chlorine becomes chloride. Or if I have something else, I have my sodium sulfate, Na2SO4. So those ions will be also going to be dissociated. So you are going to form negatively charged ions and positively charged ions. In this case, how you are going to determine the amount of the different ions? For example, if you have a sodium sulfate and sulfur sulfate, I want to see what is the ions in the solution. So in this solution, you have sodium sulfate, sulfur sulfate. So what's going to happen? Your sodium sulfate is soluble, becomes Na plus and sulfate 2 negative. Sulfate SO4 2 negative. In this case, it looks like you don't really have any other reactions except this sodium sulfate break down to 2 ions. And if you have something else, such as calcium fluoride and barium nitrate, you're also going to form ions if the compound is soluble. We already learned that most of the fluoride are not soluble, therefore calcium fluoride is going to stay as itself. Your barium nitrate is going to be break down to Ba2 negative, Ba2 negative in the aqueous. And then your nitrate, you will have 2 moles of your NO3 negative. So you have 2 moles. That's how you are going to determine the, you can say, dissociation balanced reactions. And if you imagine this way, if I have sulfuric acid, HNO3, we know this sulfuric acid is, sorry, I did nitric acid, not sulfuric acid. Nitric acid, if you have this nitric acid from your table 4.2, you know this is a very strong acid. What's going to happen? When we say strong acid, meaning this compound completely dissociated to the negative ions and is conjugate base. In this case, you are going to determine the molarity. If I have my nitric acid, this one, initially 1.4 mole per liter. How many moles per liter of your proton you have, and similarly how many moles of your nitrate. This chemical reaction occurs by 100% dissociated because your nitric acid is a strong acid. How do you solve the problems for the molarity determination of your proton, for example? So you want to know these protons, how many protons ions going to be produced. If you have 25.3 milliliter in 1.4 mole per liter of nitric acid, what you are going to do? Number one, you are going to convert your milliliters to liters. Number two, you are going to determine the moles. The moles determined by this balanced reaction. 1 mole nitric acid produces 1 mole proton, meaning the moles of proton equals to the moles of nitric acid. And then you calculate the moles by using the molarity times by the liters. Liters multiplied by molarity gives you the number of moles of proton. And then you determine the number of the proton ions. You use Avogadro's constant. So here is our solution. Solution number one, convert milliliters to liters, and then multiply by molarity, determine the moles of your nitric acid. Based on the nitric acid, which is a strong acid, meaning completely dissociated, meaning the moles of nitric acid is the same as moles of hydrogen plus proton. And then you convert the moles into the ions by multiply by the Avogadro's constant. Therefore, you can determine the proton ions. My calculation is 2.1 times 10 to the power 22 protons.